Okay, hello everyone. I'm Joscha, and today, I'm a PhD student at CISPA in Germany, the same place where I did my day. Also, is a PhD student, and today we're going to talk about unsupervised learning. And this morning, Laura gave a nice presentation about unsupervised learning, and this afternoon we'll play with some data and interpret the results and see how to make sense out of data if we don't have any labels. Today we're going to mostly talk about dimensional reduction. You already seen PCA. I'm going to introduce a new method, Tisney, just not in too much detail, but rough overview. And then we're also going to look at clustering. You discussed k-means and Gaussian mixer models in detail in the class already. And finally, we're going to implement our own version of k-means. Okay. So before we start, I'll post the link to the notebook one more time. And also in Discord, you can find the link to the notebook and the data needed. So please go ahead, open it up and upload the data. And yeah, it's wait a couple of minutes until a few persons have managed to set it up. Yeah. So if you have the notebook open and running and are able to run the first cell, like you uploaded the data, please let me know in the chat. And also let me know where you get stuck, if you get stuck. So if you run the first cell, you should see some data like that. Ah, yes. Thank you, Joscha, for sharing the data again. So the data is in the chat. You can find it on Discord. No, ignore the JPEG file. That we can delete this one. We don't need this one. Nice. Okay, we have one person. If you have some trouble, some questions that are too lengthy to post in a chat, just unmute yourself and ask. Then we can resolve it hopefully together. Nice, Samuel. Now we have two persons. 3. No, 4. 4 now, Peter. Great. And we had 5. Let's give it a few more minutes. For the people that are not done yet, are you uploading the data? Is that what's taking time, or are there any issues that need resolving? Okay. Yeah, sorry about that. It was my fault. I thought if I share the notebook, the data comes with the notebook. I had just found out that that's not the case. Sorry about taking data a bit longer. Yes, of course, we can share the link to the notebook again. On Discord, you also have to load some data set. Let me upload this again. Never mind. Did you beat me to it? Okay, and I think we have 6 people now. So I'm slowly gonna. What does that mean? Okay, I assume this means go ahead, start the tutorial or the lab. Okay, so we have some data, and for this argument, we do unsupervised learning. So we assume we don't have any labels. We do have some labels that we'll use later, but for now, please do not pay attention to them. So we have some data set. We have 4 dimensions, x1, 2, x3, and x4. So what we might do in the beginning is we first look at the data. And you've probably all seen this. You have seen some data. You probably plotted a pairwise scatter plot of the data. And then we have something like this. We see the histogram of the individual variables from a diagonal. And now we try to make sense of this data. Um, so questions we might want to answer is, oh, sorry. How many clusters are in this data set? So if you look at this data, does anyone have a guess? So we see this data with our four variables, x1, x2, x4. We just got the scatter matrix, and now we would like to know, okay, how many clusters, how many distinct classes are in this data set present? If you just this, what would you guess how many clusters are in this data set? Okay, increase alpha, hard to see. Um, okay, now we can probably see it better. Okay, so we have four. How does anyone want to explain why they chose four? And just unmute yourself and um,
Mine is it's still like I just went over the labels like X4, X3, you know.
oh, because we have four variables.
Yeah, I went over the X4, X3, X2. Yeah.
Um, uh, could you clarify your explanation? I bit trouble following what do you mean, x1, x2, x4, so on.
I mean like at the left hand side of your chart, there's like different values of X. There's X1, there's X2, X3, there's X4.
Yes.
Then they all have like uh, along the diagonal, they have like a corresponding kind of bar chart. So that was I just felt those are clusters, those diagonal charts represent clusters. Yeah.
Okay, so the diagonal is the histogram of the individual variables. You have seen this plot before, right? A plot like this.
There's like a bar chart.
Yeah. Okay. Um,
Mhm.
so I would have guessed um so I would have guessed that there's two clusters because in whichever pair of variables we look, we see two distinct groups of points. Um, yeah. Now let's look at x1, the scatter plot of x1, x2 separately, and we just look at three random points. And what would you say is how close is how close are the points to each other? And would you guess they are of the same cluster? So point two and point one. So point two here and point one. Would you guess they are in the same cluster? Just type yes or no in the chat. Okay, yes, 1 and 2 are different clusters. Looks like it, yes. What about 1 and 0? One and 0 in the same cluster? Okay, yes, it definitely looks like it. I agree with that. From this data, I would say so. Let's take a look at 3 and 4. Dimensions 3 and 4. Now, you notice something about the distance between the points?
Yeah, it changed, yeah. The point 1 and point 0 is now closer to each other.
Yes, point 1 and 0 is closer. But interestingly, if you just look at the pairwise plotting, like here, point 1 and point 0 are close. If you look at 3 and 4, I would say the distance increases. We clearly see the cluster. So the view of the data changes quite a bit depending on how which variables we look at. And this is where dimensionality reduction that you covered this morning comes into place. So now we're going to run PCA on this data set. And we have here the first principal component and here the second one. Okay, again, same question. You think we have 1, 2, 3, 4, 5 clusters? Now, if you look at this data like this, and now we look at all the data through a view of the first and second principal component. Our PCA got him. We import PCA from sklearn, transform the data, and then plot the transformed data. Is everyone able to run the cells up until this point? Yes. Wait. You have seen sklearn before, right? Okay. It's so we use the implementation provided by sklearn. And here we just plot the first 3 points to look at these points. Okay, seems like everyone is able to run it. Can everyone post in the chat how many clusters they would say are in this data set, given looking at the PCA embedding? 2? Yes, 2 sounds reasonable. Seems like we have an agreement on 2. Okay. Yep. 2 will later look at the ground truth. But I agree, from what we see in the data, very much looks like 2 clusters. Okay, now we'll take a look at a different embedding method called t-SNE. I'll explain that one first, and then we can run t-SNE on this data set and see if our interpretation changes. So, t-SNE, I'm still able to see my slide, my screen? Or not? Oh, yes, you're also able to see it. Perfect. Okay. I'm not going to do too much detail here. It's just about the general idea. So we'll not really look at the math. So if you have some data in some high dimensional data space, like 4, 5, 6 dimensions, we want to essentially find a representation of this data in a lower dimension. For example, 2 or 1 or 3 dimensions. You discussed this earlier with Deborah. Is the goal of going from a high dimensional to a low dimensional space, is this clear for everyone? Okay, so we have our data in some high dimensional space. For each data point, we set a Gaussian distribution onto this with the mean of the data point. And then we have our distribution. It's like visualized here by the circle. And we do this in the high dimensional space. And we do the same in the low dimensional space. And our goal is to preserve the probability of the neighboring points. So xi is yi in low dimensional space, and the distance from xi to xj, or respectively yj, should be the same in the high and low dimensional space. Of course, you cannot just go from the high dimensional space to the low dimensional space without losing information. So you want to get as close as possible to that. We use a Gaussian distribution, so a normal distribution, and we center it around our point. And what we see is, okay, if we wanted data points that are very close, have a high density in terms of our distribution, and data points that are further away have a lower density. And if we get into the tails here, the density is extremely low. So it's much more important to get the points that are close, the right distance, than the points that are far away. Because far away, it does not really make a difference if you are here. The probability, the density is essentially very similar to a point that is all the way in the end. So where in the tail, the density does not change that much anymore. Whereas if the points are closed, the density should match as closely in the low dimensional space as in the high dimensional space. Are there questions to Tisney? Did you get the general goal? What it is? Okay, so we have points in our high dimensional space. Around each point, we set a Gaussian around that point, and this gives us a density for all neighboring points, or for all points in the data set. And close points will have a high density, and further points will have a very low density in our distribution. So if this is our point, and the closer the points are, the higher the density. And if they're further away, the density goes down. Now we do the same in low dimensional space for all points. We do this for all points. And our goal is to preserve the density between the points as much as possible. So we have an optimization problem. And through how this density works is, I actually lied. It's not a normal distribution. It's a t-distribution, but let's just think of it as a normal distribution. Yeah, so if And if a point is further away, it would have a very low value here. And then it does not really matter if we put it in a low dimensional space. If we put it much further away than it actually is, because it's going to stay low. And so the entailed penalty for the mismatch is very low. But points that are very close, there we have to preserve the distance very well. That's the general idea of t-SNE. So it goes from, essentially it takes a local view on the data. It wants to preserve the distance of the points that are close and does not really care too much about the points with a large distance. Okay. Again, any questions on t-SNE? Okay, then we can come back to our notebook. And sklearn also implements t-SNE for us. However, there are some hyperparameters to choose. And one of them is the perplexity. And in a nut, this essentially is to which degree do we pay attention to close points and further away points. So the lower the perplexity, we only look at a very small neighborhood, and if we increase it, we look at further away. So you probably have seen k-nearest neighbors. Think of that as a similar knob that you can adjust. So now I would like you to try out, play a bit with the perplexity value, run the cell, look at the output, and yeah, then report back what you found. Shall we take 5 minutes for that, for everyone to just play around with the perplexity, also with the random state. So it's an optimization problem that you can change the random state. Maybe that changes results as well. Okay, everyone, please play around with the perplexity, and then we will interpret the results together. See you all in 5 minutes. Yes. Can upload the data set. It's on Discord, and I'll upload it right here into the chat. You can start with 1 and knock yourself out. The default value is 30. And if you go too high, you will get an error message. Can play in ranges of like with integer. Okay. Seems like we have some results. No, we were taking a 5-minute break so everyone can play with. Can you hear me? Oh no. Yes, can. Um, Everyone can play with the perplexity of Disney. So we have some results in the chat. Um, how about we? Okay, try some perplexity. We have 141. Let's try this one out. Takes a few seconds. Okay. Sorry. 141. What else we have? 20. That looks very similar. 41. Let's try 41. Yes, 11. 11 is interesting, right? Let's look at 11. So if you look at this data, which keep in mind is the same data we have been looking at all through this, we ask you again, how many clusters do you think are in this data set? What would your interpretation be? Just post your guess into the chat. 4. Okay, I assume we're counting 1, 2, 3, 4. Yes, looks like 4. So now, if we change the complexity to, we had 50 or 40 earlier. Would you still say 4? 2. Okay, and now we're running into the issues that we have with unsupervised learning. We're always looking at the same data, and the number of clusters ideally would be the same. But depending on how we plot the data and how we interpret our plot, that might skew our view onto the data. For example, if I make a more extreme example and set the perplexity to 1, we get something like this, which we could have 1, 2, 3, 4, 5, 6, 7, and so on clusters, which also doesn't really make sense. So that's the big difficulty in unsupervised learning. We never really know when we're correct, and what the true number of clusters is in the data. If we, for example, plot 20, oh, no, I changed the wrong thing. Enter complexity to 20. Then it looks much closer to the 4 clusters, maybe. If you want, you can also see a bit of a cluster here, the cluster here, or 1, 2, 3, 4, 5 clusters. So it's quite difficult to make sense of just looking at an embedding. Let's take a look at different data set, which is a bit more clear about the ground truth. So here we have a data set with just 2 dimensions, so we can directly plot it. Same questions again. How many clusters do you think are on this data set? one cluster. Okay, two. Okay, we have 1 and 3 2s. So the 2s take it. I would agree it's 2 clusters. So this is clearly 1 cluster. And this is 1 cluster. They're just not, we cannot separate them very well with a straight line, essentially. Now, and this is for demonstrating purposes. Now it's 2-dimensional data, so we can look at it and kind of see that there are 2 clusters. Suppose this data is now 10-dimensional, we wouldn't be able to plot it. So we would run PCA, and for this argument's sake, I'm running PCA down to 1 component, and the other dimension is noise, and I plot it like this. Can someone explain what goes wrong here? Or here you can see not 2 clusters, I would say. Why does the PCA result look like this? Anyone? Or maybe one can start with a short summary. What does PCA do from this morning? Does anyone remember what PCA does in a nutshell? Essentially asking the question, okay, if we plot this data here in dimensions, we see, I would say, 2 clusters. 1 ring is 1 cluster. Now, suppose this is higher dimensional data with, let's say, 10 dimensions. We couldn't just plot it and look and see it. How many clusters there are, what the data would look like. So we apply a dimensional reduction method like PCA. And well, now we find this is our dimensional reduction. And as we can see, so we projected it down to 1 dimension from the 2 to 1. Now, I would say here it's hard to see that there are 2 clusters. So essentially, I'm asking, why is that? Why did PCA not fail? But why does the result look like it does? Why don't we see the 2 clusters anymore? Maybe we can go one step back. Can someone summarize what PCA does in general? Okay, let me rephrase the question. Yes, and yes, it does reduce the technology. Yes. How does it do that? What does the first principal component represent? Yes, I'm changing it to yes. Yeah, Tejo. The first direction is the first principal component is the direction of the highest variance in the data. So if you look at this data set, okay, variance is fairly uniform, but we probably have, let's say, just for argument's sake, this is the direction of our highest variance. Can I sketch here into this? Oh, nice. Let's change it to red. Let's say this is our direction of the highest variance, just for argument's sake. Now what happens is PCA, we project it down to the first, as we go from 2 dimensions to 1, all this data gets projected onto this line. Like so. Now, if we plot this line and how do I remove this now? Okay. So if we now project all this data onto one line, and do remember that this dimension is just noise, otherwise it was just be one line, we don't see any structure anymore because the direction of highest variance goes through here, all gets projected onto this one line. Now, what happens if we run t-SNE? I'll just run it. Again, takes a bit of time. It's an optimization problem. And then it's just a blue line if I remove the noise. But we can it's worked. So now our t-SNE is done. And how would you interpret this plot? And keep in mind, this dimension is just noise. Let's include the labels. So as you can see, if we include the different classes, like do the same here. So the yellow is the inner ring, the purple is the outer ring. If we plot it, project it down, you see we have a mix of yellow and purple, but we can really differentiate. Now we do the same with t-SNE, and even if we don't know any class levels, we see there's a weird gap here. Plot the labels again, and yes, exactly. If you see now in the chat, you see that t-SNE, it's still running for me for some reason. Okay, yeah, you can clearly see t-SNE is able to separate the yellow class from the purple class. How does it do that? By only paying attention to data points that are closest. And the closest for each data point are the ones within its own cluster, even though the cluster goes around one time. And even if you project it down to one dimensions, it's able to separate two classes mostly. There are some outliers here that misbehave. This is, however, just the half true, because if we just kick all this out and run it again, we see it does some weird clustering where one cluster on the right-hand side, and then some yellow in between with one line of purple in between, and then with purple again. So t-SNE is quite susceptible to its hyperparameters, mostly perplexity, and then how long do we learn how to learn it. We'll focus not on that today. So with t-SNE, you have to be careful. The results, as we have seen in the past few examples, can change quite radically how you adjust your complexity. But if you pick it just right, you are often able to separate classes that PCA is not able to do. Okay, now we're going to run. Are you all following along? Are you able to run the cells? Okay. Seems like we lost many of you. Are there any questions? Anything not working? Servers running good. Okay, so okay, people are still running their stuff. Any challenges? What does that mean? Okay, I see. I would say it's mostly about interpreting results today. Because yeah. Okay, now let's run t-SNE and PCA of the MNIST dataset. So MNIST dataset are these handwritten numbers, and we want to each dimension essentially is a pixel. Can I show it? Yeah. Okay. So essentially each file, each number consists of like 700 pixels. So we have like 700 dimensions. And now we would like to visualize this data set. Okay, we could run PCA. So we run PCA on the first 3,000 columns. And let's see what happens. Okay. Does anyone want to interpret this plot for me? Okay. Why did you use error on which side? Okay. Yes, we have, well, okay, I'm not sure why you say it's 4 clusters. If you don't see the colors, say there's 1 cluster. But essentially it shows that PCA is not able to pull the different clusters of numbers apart. So we have essentially 10 classes, 0, 1, 2, 3, 4, and so on. Yeah, but okay, the different colors are the labels already. And yes, we see some cluster of labels, but in unsupervised lossing, we usually don't have these labels. So right now we're plotting the label with the labels. And if we now plot uses Disney, we see are able to get these clusters. There's still some clusters that are a bit mixed, but usually we get much cleaner clusters. Okay. So if you really have high-dimensional data and your PCA does not give you good results, I think it's worth trying out Disney. We'll have to play a bit with the perplexity and the random state, mostly the complexity. But I think you can get much cleaner clusters than PCA in some cases, if you want to visualize your data. Okay, Elijah, glad to hear you got it to run. Okay, now we have seen Disney and PCA. Let's go back to our original example where we're exploring our data. Because we do actually have the target. Turns out there are actually 3 clusters. So this is the iris data set, probably heard of. And there are 3 different kind of flowers. But admittedly, it's very hard to see in PCA. So I'm adding now the labels. And we can see now when we plot it with colors, the clusters are quite clear to see. The difficulty in unsupervised learning is there are you don't have these clusters. And essentially want to answer this question just on the data. If with t-SNE, we are often able to get this a bit more out, but there the difficulties are finding the complexity. For here, we get fairly separated clusters. And yeah, we looked at this one already. Okay, let's take a break, everyone, for 10 minutes, and see you all in 10. Okay, welcome back, everyone. Were you able to get some new insights? A break? Something you found out about the data you would like to share? So Teju shared this one in the chat of the universe. So which, oh, still trying to upload. Okay. It's a bit large. If you want, you can, we're only looking at the first 3,000 columns. You can essentially cut the data short if that helps with uploading. So just delete everything that's not the 3,000 first lines. Okay, coming back to this plot, where we see the numbers. And you can see that the 4 and the 9 and the 7s are kind of, well, the 7s are mostly here, but some 7s are in there. The 4 and 9s are quite merged together. Anyone, any idea why that is? So why do we see the 4s and 9s essentially somewhat together in one cluster and not clearly separated as the 2s from the 8s from the 3s? Maybe it helps if you think about the shape of the numbers if you write them by hand, because keep in mind the data set are a bunch of handwritten digits. Okay. Okay, maybe yeah, a little bit. How similar is 0 to 1? If you look at the handwriting, the shape of the handwriting, are they very similar? Yes, not similar. Okay. How about 4 and 5? How similar are they? Yes. Okay, now we go back. So thank you, Toshiko. Toshiko. Sorry about your name. Thank you for answering. Tosi, hi. Okay, good. So now we look at 9 and 4. To draw them by hand, would you say they are similar or not similar? Everyone? Yes. Yes, exactly. They're quite similar. So if you go here to the handwriting, what was it for? 4 and 9. 4 and 9. 4 essentially is a 9 with the top line missing, roughly speaking. So asking again, yes, 9 without a cover. Exactly, Elijah. So now, why do we see them together? Yes, because they're similar. Um, and essentially, yes, exactly. They're essentially the distance they have in the high dimensional space is not as large as the distance between 9 and 8, for example, or 9 and 3. They're apparently in the high dimensional space, they're quite different. Whereas 7 and 4, 9, sorry, 9 and 4 are surprisingly similar in the high dimensional space. And this information gets projected down to in the low dimensional space. Okay, just as a extension of Disney. Thank you, Teshu, for sharing this plot. Okay, now we'll move on to clustering. We start with k-means clustering, and we look at our same data set as before. I'll start with one cluster, and what I'm doing here is, so we're using the data frame from the beginning. So now cannot show it. Our data set with our four variables, and where we already revealed that we have 3 classes. But suppose we don't know that, because in unsupervised learning, we don't know that. So I'm using k-means from sklearn again. I initialize it and set the clusters to 1 initially, just so we can look at the data. Yes, I'm getting to the PCA in a second. So we run k-means and we get a label for each point. In this case, the label is all 1 because we only have 1 cluster. You want to unmute yourself?
Yes. So it seems like you're just you're using XPCA, which may have been overwritten by the MNIST one. I'm not sure, or maybe it's just for me, because when I try, oh no, you have a different name. Sorry. Then probably it's just for me because I tried to run it and I got an error. So I thought maybe you need to rerun that. But it's okay. I'll just rerun the cell. Probably I ran something else and everything messed up.
Yes.
But I rerun the cell, but I'm still getting an error that says it's from this plotting. It said something like index 1 is out of bound for axis 1 with size 1. I think it's from the plotting. Oh yeah, because XPCA, you tried X 1 dimension, I think. At some point, so we need to go back to when.
Okay.
So you need to change this. You need to maybe just copy the PCA part back and rerun that and make NPCA to be 2 dimension.
So
I think that
everyone scrolls back to this cell.
Copy it and paste it. to the source of
Oh,
error.
each PCA noisy circles.
Uh,
Yes. Why is it working for me then?
it's working for you, is it?
For some reason it is.
Okay. No, sorry, should not be noisy cycle. I'll try to fix it and send a solution.
No, it's many people have this problem. Please run this cell again.
Which one?
Anyone? This one in the PCA, just the very top of the notebook.
Just a moment. Oh yeah, I see.
Is everyone able to find the cell?
I think I just quickly copy pasted. I think you were talking about. I found the cell. So this is what you said we should run again, I think.
And if you run the cell and then go back to the run cell that got you an error, are you able to run it?
Yes.
Nice, good.
So just to troubleshoot the error, the problem was that you named the circle example the same. So
Yes.
this became, so maybe you just have to update the notebook for the final version and change the name so we don't run into an error.
This one.
Yeah, I think this was the problem.
Okay.
Yeah,
I'll make another pass
fine.
before we check. Okay.
Thank you.
Everyone able to resolve the issue by running the cell? We have 2 thumbs ups. Good. So if you come back to this one. So we're running k-means. Why am I still using PCA? Can someone unmute and explain? So to recap, we run k-means just with one cluster for now. Fit it on the data, and we get for each data point a label. Why am I still using PCA to show the result? We're doing k-means now.
Wow, I can go. People are shy, they're not talking. To reduce the variance. No, this is not what k-means does, right? Because remember in the morning we said we can use the k-means algorithm to find the number of clusters that exist in our data set. And it seems like right now we just try to find the cluster. From what I can see from this code is that you use it to find the number of cluster, and you are plotting. You also now reduce the dimension of the data into 2. I think we have to bring it back. I like it's confusing. So maybe you need to show us any dimension you reduce the PCA to first, so that it's been a while since we talked about that. So maybe just to copy back the cell to know how many dimension it was. Was it 1? Was it 2? I think you had 2 in the beginning.
2. Yes. So we are running k-means on the data set with still the 4 variables.
Yes.
And the plotting here is just that we can look at it because we still cannot plot the 4 variables. That's why for what I'm using PCA here.
So this is what you're using PCA for, just to look at 2 variables, but
just to look at the result
just to look at the results.
Because I cannot look at the 4-dimensional data. I cannot plot this.
So the correct answer here would be for visualization.
Yes, for visualization. It's just a practical way to, if I run k-means on my full high-dimensional data, I still kind of want to often visually inspect my results. And PCA or t-SNE would be then one nice way to project my data into a lower dimension and just look at it. Okay.
Okay.
Now
thanks.
let's run k-means with 2 clusters and see what we find. As expected, we find 2 clusters, and well, it's reasonably happy. All what's a bit annoying are these yellow points. But I think we can live with that one. In the lecture this morning, you discussed something about an elbow plot. If I run now k-means for clusters going from 1 to 11 and plot the inertia, so the square distance to the centroid, we get the following plot. If you look at this plot, where would you say is the elbow? Can you post in the chat if we have an elbow at 1, 2, 3, 4, 5, 6, or 7? Like, where's our elbow? 4, 2, 3. Yes, I would say it's okay, 4. Okay, we have 2, 3, and 4 as options. So let's look at the individual results. This is with 2. Now we run it with 3 clusters. Find this. And finally with 4. I don't think anyone said 5. Well, by now we can kind of remove the points. I think we're done with these. Okay. Now that we have seen our 2, 3, and 4, does anyone want to change their number of clusters that make sense? It's 4. So one of these settings, it's very difficult to know the ground truth here. It's the same data set as we've been using earlier this tutorial, so we know the ground truth is technically 3. But we can also see the split in 3 does not really make sense. It's a bit arbitrary, like if this point, whether to which clusters belongs now. It's just creates a weird line through the middle here. And even elbow plot, always somewhere between 2, 3, or 4. I would say they're all valid answers. If you do not know the ground truth, none of them are obviously wrong. So this is a bit of the difficulty in unsupervised learning. to actually know which one is the true one. Very difficult to tell often. What we can clearly see, there's at least 2 clusters. And if these are separate clusters, it's hard to tell. If you look at the elbow plot, 3 or 4, 2, 3, and 4, I say, are equally reasonable choices here. Now, we do the same with our Gaussian mixture model, which you also saw. Let's start with 2 again. Two, at least these now to the other cluster. Let's look at it with 3. You see the Gaussian mixture model there's creates some new clusters that I find make a bit more sense than what k-means does. Now let's look at our elbow plot again. This time we look at the log likelihood score, so it goes up. What would be interesting values to try out in this setting? If you look at this plot. 2, 3, 4, 5, 6, 7, 8, 9, 10 maybe. Please post in the chat like how many clusters you would choose based on this plot. True? Two and 4, 3. Two or 3, okay. No one wants to go for 10. Okay, we've seen 2. This is 3. 4 was also an option. Let's try 4. Okay, 4 is very interesting. Why do we see this mix here? This one to out again. So with 4 clusters, we see the purple and the green ones are kind of mixed. How does this make sense if you think back how the Gaussian mixture model works? Why do we see this here? I'll give you a hint. It has to do with the PCA embedding. Okay, so the answer essentially is we're not looking at the direct clustering, we're looking at the embedding again. And that's why we see these points that are essentially interleaved between green points. Yes, exactly. In the true data set, we have more than the 2 dimensions. So we see in the projection, it looks like they are interleaving. In the high dimensional space, they don't do that. They have their nice Gaussian distribution. Okay, and to be honest, I'm kind of curious about 10. So I'll try this, and I've not done this in the preparation, so let's see how wrong this goes. Okay, 10, everything is mixed. Okay, if I look at it, I don't like it anymore. So I think 2, 3 are the very sensible choices here. As most of you suggested. From the elbow flow, 2, 3. It's actually very difficult to tell apart if there are 2 clusters here or not. Okay, and now we'll start to implement our own version of k-means. So back to our from k-means from the lecture, we had this Lloyd's algorithm, and we initialize. So for this, it's not as you implement along, will be implemented together. So if you have not been running our cells, now is the time to get the notebook out again. And we want to implement this Lloyd's algorithm. As a quick recap, we initialize our centers, usually randomly, or one of the strategies randomly. And then we go into a while loop and update our centers while they are changing. We assign, as a recap in the loop, we assign all points to their closest centroids, compute the mean of the center, and update the centroids. Okay, let's implement it together. We have all these functions, and you should be able to, well, nothing happens here yet. Okay, what's the first thing we have to do? The centroids are not none to the beginning. What is the first step in our Lloyd algorithm? Okay, we pick k random centroids, and we start. So out of all x, we choose essentially k, and we do not replace the data set. So we have now k random start points, our centroids. Does everyone have that? So now we initialize our centers. Now, while it's changing, we have to update our steps. So now we need to know if our labels changed, if we want to write a while loop. So we start, let's copy our while loop, and initially our labels are none because we have not assigned anything yet. Well, and now we kind of have to check, are our old labels the same as our new labels? The first iteration is a bit odd because we don't have any labels yet. Well, we do have the labels from the samples. But let's just create one. Old labels, also set none. And we want this repeat. This is now a case to cover the first case, while old labels is none. We want to iterate. Or if there was a change between the labels within iterations. So if the labels change, this is array equal, yes. No, it's labels. So as long as these not, as long as these two arrays are not equal, we want to continue our update steps. Now, how do we update our centroids? What do we have to do in this while loop? Can someone unmute and explain what we do in the while loop of k-means, or the I forgot the name, Lloyd's algorithm? Okay, group or something according to the closest. So we first have to know what the closest is. And for that, we compute the distance to all our points. This one was the square root, right? Of the square root of 2. And for each data point, we subtract the centroids. Pay attention to the brackets. The sum of that over x is 2. So essentially compute the distance to all our data points. And our labels are then simply the one with the minimum distance. Now we have newly assigned labels. Now it's time to update the centroids. So for each centroid, so we have cake centroids. Centroid J is, we select all data points that are labeled with that centroid. And take mean of these. And this, we update our centroids. And that's already it. That's implementation of k-means. Now, if we, for example, run this on this toy data set with the 3 clusters, oh, did I make a mistake? Not supposed to take this long. There's a
Hello, can you hear me?
hello. Yes.
I don't think you included the maximum iteration in your while loop, so this is probably going to run forever. So I suppose you wanted to go to stop
Max iteration I
also.
wanted to implement later,
I see. Okay.
that we can look at the individual steps. So,
okay.
but I made some mistake. Oh, I forgot to update the labels. Of course. Old labels are the ones we saw one iteration earlier. Otherwise, the labels never change. Okay, now this should work. Oh, it's wrong. Oh. And you see the labels. So we plot the labels. We see the centroids. Very nicely clusters our data. Now, what can go wrong with k-means? I had to play around to find some seed, but something like this can happen. Does anyone want to explain what went wrong here? Yes, essentially, we got unlucky how the points were initially chosen, and then it converged to a solution where it puts these two clusters into one cluster, and the one cluster split over two centroids, which we obviously do not want. Let's include the max iteration and see how k-means works in practice. So max iteration. So we need to count how often we go through our loop. And if we only want to continue if the iteration is smaller than our max iteration. Where is it wrong? No, it's gone. Okay. weird since we update our centroids in the end. We kind of have to make sure we do not update our centroids if the iteration is set. Only if it below the max iteration. So we include this if iteration kleiner, smaller max iteration. Now we go back here and we set max iteration to 1. We run it for 1 iteration. You can see, okay, this is how it gets initialized. It's very close to the end already. Let's try this one. Something is wrong. Oh, large or equal. Other way around. Now run it. Yes, you can see initially all our clusters are here. And then step by step, the clusters get updated. So it has 2 steps. See this. After 3. This is working properly. Oh, still some bug. Yes, of course. I count my iterations. There's a question. Yes.
Yeah, so I just want to say that would maybe you put the iteration count as a for loop so we can see as the plot is changing instead of you like changing it one by one and forgot what it was in the previous iteration. It's just a suggestion.
Yes. Just quickly, let me check.
The
Okay,
name
now.
as it's supposed to be iteration. Yeah. Should be fine for it now. No.
Where is it program?
Shouldn't it be inside the if, not the
Oh yes, we want to
count
have
when you're counting it. Okay.
Changed it from correct to wrong earlier. Yes. So start 1 iteration. Yeah, we start here.
Also fixed.
And this is after 1. Okay. Yes. Put this into yes, we can put this in a for loop. Let's look at 4 iterations. Oh.
No, I don't think you're changing it, Joscha. So because maximum iteration is still 2, is that intended? Like it should be like my idea is for I in range of 4. Okay,
yes.
you're using
I'm doing that. Yes, now it's working. Okay, let's start with 1 iteration. we see all our clusters are here. Then after the second iteration, clusters already got massively updated since all these points pull the mean over here, and these points pull this cluster over here. And the third one, we already reached convergence. That now there are no more clusters from the one cluster as was still here. And if we update the clusters, we're not going to see any changes. So if you go to 5, there's essentially no difference between the last two. Okay. And we're almost at the end. Just look at this data set. And, well, how do you think k-means is going to behave there? Very badly, as we can see. So we start all there again for some reason. The clusters are pulled apart, but never really able to pick out the individual clusters. And we kind of end with that, where we split the two clusters into two centroids that we don't really want. Whereas this one is fairly okay, but still we have some points assigned to this cluster where they obviously belong to this one. You can run this for two. So convergence. Just to see the results. Yes. Yeah. Gets a bit better if you run a bit longer, but we still have these clusters split, the centroid split over the different clusters. Okay, were you all able? Yeah, we'll share the notebook. We're out of time now. And yeah, as you can saw, the implementation of k-means can be very straightforward. Yes. Any questions? Okay, if not, let's say we can end it here. You've seen now. Yes.
Yeah, no, I just wanted to wrap up. It's fine if you want to say something. I'll just wait.
No, I'm kind of lost. Okay, go ahead.
I was just gonna thank you again. I thought you had already wrapped up the class. Is there any question for anyone still remaining in class? Any question? Something you want to talk about now? Or not? Okay, seems not. We have a bit of a quiet audience today. It has been a great class. Thanks, Elisha, for the positive note. Like given our tutor some nice vibe at the end of the class. So, okay, yeah, this is it for unsupervised learning. And next week we would be having a class on lecture on a tutorial as well. I would have one of my dear friend, mentor, big sis, Yetunde give it a talk, not a tutorial. She will give a tutorial. I keep saying tutorial. She'll give a talk on recommender system. That should be what we have for next week, I suppose. Let me quickly confirm, or maybe it's Futse. No, is it Futse? I'm mixing things up. Oh, sorry. Futse gives recommender system in 2 weeks' time, but next week, indeed, Yetunde Sani would be joining us to talk about decision trees, interpretable models, and we would also have a lab following that. Oh no, there's no lab next week, but there's lab for recommender system. Yeah, as you can tell, I'm mixing things up here because I thought like maybe we had a lab next week. So I have to always go back to the GitHub repository that I prepared to remind myself of the program. But the most important discussion is that we're slowly moving to the end of the cohort 8. I know it's a bit of a ride. It's almost like we're in our 3rd month now, right? We started in August, and this is already November. Time flies. So we have approximately 5 weeks till the demo day. So we will send information following like the instruction about the project presentation, which is scheduled for 16th of December. And yeah, looking forward to seeing you guys next week for yesterday's class on decision trees. And enjoy the rest of your afternoon or day, wherever you are. Thanks again, Joscha, for being here.
Thanks everyone for
Bye.
joining. Bye.